All right, class. Good afternoon. So we'll proceed to the other topic in machine design. So which is the shafting. Okay. So this is class an application of the fundamental principles in machine design. Okay. So let us now consider what is the definition of a shafting. So a shaft is a stationary or rotating member having circular cross section and usually equipped with gears, pulleys, flywheels, sprockets, cranks, and other power transmitting elements. So the shaft may be subjected to different types of loading such as compression, tension, bending, and torsional loading. So the load may be act on the machine member singly or in combined manner. Okay. So next is the fundamental equation of the induced stress. Okay. So, designing shaft under pure bending. So, by this time, class, we're going to consider only a bending load in a shaft. So, in the analysis, the induced stress is equals to the flexural stress, where the flexural stress is basically is sigma F is equals to MC over I, where the M here is the maximum moment. C, of course, is the distance from neutral axis to the outermost fiber. So that is the diameter divided by 2. And of course, I is the moment of inertia. Okay. So next is for solid shaft, the derived equation, of course, is 32m over pi d cube. So actually, class, you can use the equation TC or MC over I. So where I is equals to pi d to the fourth over 64. Okay? So in order to derive this equation, class, so I is the moment of inertia equals to pi d to the fourth over 64. Okay? So, and then substituting the values, of course, from the flexural stress. So, and then you will get an equation which is 32m over pi d cube. Okay? So, for hollow shaft, so flexural stress equals to 32m multiplied by d over pi d to the fourth minus d to the fourth. Since, class, the moment of inertia is equals to pi over 64 multiplied by d to the fourth minus d to the fourth, or the outside diameter to the fourth minus the inside diameter to the fourth. So that's why, class, we have here the sigma F is equals to 32m over pi d cube. Okay, so where this factor 1 over 1 minus k to the fourth came from. Okay? So, here, class, you are going to okay, in this equation, we are going to eliminate the diameter inside or at the numerator by multiplying at the numerator of d to the fourth over d to the fourth. Okay? So, where that d to the fourth, big letter d to the fourth over big letter d to the fourth is just equal to 1. Okay? So, it does not affect, of course, the equation. So in that manner, the diameter at the numerator d divided by d raised to the fourth will become 1 over d cube, which is now this d cube here at the numerator. Okay? So, knowing that k is equals to small letter d to the fourth over d to the fourth. Okay? Or d rather, small diameter divided by the big diameter. That's why here, d to the fourth divided by big letter d to the fourth will become k to the fourth. Okay? So, take note class that you can only apply this factor if the shaft is hollow. So, take note of that class. So, this equation is for shortcut method. Okay? So, for solid shaft, under pure bending, 32m over pi d cube, and if it is hollow, multiply this by 1 over 1 minus k to the fourth. Okay? So, you have to derive this class in order for you to become an expert, of course, how you are going to derive the equation for shafting under pure bending. Okay? Next class is design stress and factor of safety. So, for ductile materials class, that is flexural stress is equals to the design stress equals to the yield stress over factor of safety. And for brittle materials, that is sigma F equals to sigma D equals to the ultimate stress over factor of safety. Okay? And then, shaft under pure torsion. So, take note class, this is also basic. So, the analysis or the stress acting, of course, for a shaft under pure torsion is torsional stress, where the torsional stress, the basic equation is TC over J. So, this is no longer I class, but this is J, where J is the polar moment of inertia rather. And T is the torque transmitted, and C is, of course, the distance from neutral axis to the outermost fiber. So, knowing class that J equals to pi over 32 raised multiplied by d to the fourth for solid shaft, and J equals to pi over 32 d to the fourth minus d to the fourth for hollow shaft. And then, substituting class the equation, you will derive an equation tau is equals to 16t over pi d cube. And for hollow shaft, you just multiply it again by a factor 1 over 1 minus k to the fourth. Take note class, this is shaft under pure torsion. Okay? So, let us again consider the materials for ductile. So, that is tau or the shear stress equals to design shearing stress equals to the yield stress and shear over factor of safety. So, for the yield stress class in shear, that is the yield stress and tension multiplied by 0.5. Okay? So, take note that the shear stress equals to the design shearing stress equals to the ultimate shearing stress over factor of safety. Okay? Again, class for torsional deformation. Of course, if the limit or the torsional limit, of course, is reached, or maybe the actual value of the torsional deflection is greater than the torsional deflection limit, of course, the shaft will fail. Okay? So, class, again, getting J, again, is the polar moment of inertia, and then substitute to the equation. So, take note, class, that theta here is in terms of radians. So, usually, the required is in terms of degrees. Okay? So, you know already that class that 180 degrees is equals to equivalent to pi radians. Okay? So, next is shaft under combined loadings. Okay? So, for shaft under combined loadings, ductile shaft under bending and torsion. Okay, by maximum shear stress theory. Take note, class, if the shaft is undergoing a load which is torsion and bending, the theory that you are going to use, of course, is the maximum shear stress theory. Okay? So where that maximum shear stress theory is the maximum shear of the shaft is defined in terms of the shearing stress and the flexural stress. Okay, the equation now is tau max is equals to the square root of the flexural stress over 2 square plus the square of the shearing stress. Okay, so again, class, knowing that flexural stress is equals to 16t over pi d cube, and then flexural stress equals to mc over I, and then substituting that equation here in the maximum shear stress theory, and then you will get a value of tau max equals to 16 over pi d cube, and then square root of m square plus t square. So but what is this square root of m square plus t square? So this is the maximum torsional, okay, okay, so torsional moment, okay, so or equivalent twisting moment. Okay, next we have here, okay, the equivalent twisting moment equals to m square plus t square, or designated as TE, and then substituting class the square root of m square plus t square by TE. Therefore, the maximum shearing stress under combined loading is 16 TE over pi d cube. Take note, class, for solid shaft. But for hollow shaft, you multiply it again by 1 over 1 minus k to the 4. Take note, class, that the shearing stress maximum is equals to the 1/2 of the yield strength, okay, over the factor of safety. Okay, so ductile shaft under bending and torsion. So this is, class, the other for brittle materials. Okay, for brittle materials, we use the so-called maximum normal stress theory, where the maximum normal stress theory, if you look at the book of Berhel-Moring Fairs, so you will see this equation. Okay, so where that equation is the flexural stress, or the maximum flexural stress, is equals to, or the normal stress rather, equals to the flexure over 2 plus the square root of, okay, so this is, class, the maximum shear stress theory. So plus, so maximum normal stress theory is equals to maximum shear stress theory plus the flexural stress over 2. Okay, so then substituting again the equation for sigma equals to mc over I, and then tau is equals to 16t over pi d cube, and then the equation will become the maximum normal stress equals to 32 over pi d cube multiplied by 1/2, or the factor 1/2 multiplied by m plus square root of m square plus t square. Or this factor, class, is the so-called equivalent bending moment, which is designated as ME. So if you substitute that expression, that stress now is equals to 32 ME over pi d cube. Take note, class, this is again for solid, but for hollow, multiply it by 1 over 1 minus k to the 4th. Okay, so take note, class, the maximum normal stress equals the ultimate stress over factor of safety. Okay, so shaft code, class. Okay, so take note, class, that this equation here is derivable. Okay, this is derivable. Okay, so this is under the ASME code and also the PSMA code. take note class that for main power transmitting shaft, the stress considered is 282 kilogram per centimeter square, or that is equivalent to 4,000 psi. Take note class that the factor of safety considered for the main power transmitting shaft is 15. Imagine class that the factor of safety is 15. So take note that if maybe the stress will be doubled, tripled, and so on and so forth, it is very difficult class to fail because the factor of safety is 15. Okay, take note class. So I will not, but the equation here class is very easy. The equation considered is power is equals to 2 pi Tn over 60. Okay? Or Tn over 630, 25. And also, shearing stress equals to 16T over pi d cube. And then substitute class that equation, and then you will derive an equation which is D equals to the cube root of 80.2 horsepower over N. So you can class easily determine the diameter of the shaft if the horsepower and speed of the engine are known. Take note of that class. Okay? Next is for the line shaft carrying pulleys. Again, class, that the shearing stress considered is 6,000 psi or 423 kilogram per centimeter square. And the factor of safety considered there, class, is only 10. Okay? So that is why the derived equation, again, knowing that power equals to Tn over 63025 and shear stress equals to 16T over pi d cube, and then substitute, the formula will become D equals to the cube root of 53.5 HP over N. And for the last type, for the last type of shaft, so this is small or short shaft, okay, or the counter shaft. Take note, class, that the shearing stress considered here is 599 kilogram per centimeter square, or equivalent to 8,500 psi. And the factor of safety here, class, since the shaft is very short, the factor of safety considered is 7. And substituting again the value, power equals to NT over 63025, and then the shear stress is equals to 16T over pi d cube, you will arrive to the equation diameter equals to the cube root of 38 HP over N. Okay? So take note, class, that the formulas that you are going to consider here in is shafting topic are it is not only one, but there are so many formulas that you are going to consider. Okay? So next is for ASME code, class, using the fatigue and shock factor. So take note, class, that this is the maximum shear stress theory. So that is 16 over pi d cube m square and then t square. Take note, class, if the moment or the factor for the moment is, or km rather, is considered, you are going to multiply this factor to the moment. Okay? Same as for shear, okay? For torque, okay? You multiply also the factor for torque and then square it, okay? Same as here for maximum normal stress theory, okay? So you will only consider Km, of course, to the moment, and then Kt to the torque, okay? And then next is shafting design by machinery handbook. Okay, so there are several So there are several conditions here that we are going to consider. Take note, class, that for a lovable twist not exceeding 0.08 degree per foot. Okay? So the diameter is equals to 0.29 and then to the fourth root of t. Okay? So this is class an empirical formula. Okay? And also, d is equals to 4.6 to the fourth root of hp over n. Okay? So, and then for is a unit, so that is d equals to 2.26, the fourth root of t, and then d equals to 1.25 or 125.7, the fourth root of p over n, and then for allowable twist not exceed 1 degree per 20 diameters length, okay? D equals to 0.1 cube root of t, and then d equals to 4 cube root of hp over n, okay? So, another formula, class. And then for short solid shaft subjected only to heavy transverse shear. So, diameter equals to 1.7b over the shearing stress. Okay? Or the torsional shearing stress. And then the maximum distance. So, shafting subject to no bending action except its own weight. Okay? So, L equals to 8.95 the cube root of the square of the diameter. Okay? Shafting subject to bending action of pulleys. Okay? That is equals to 5.2 cube root of the d square. Okay? Thank you very much, class. Okay? Thank you.